This is the fifth shorter video on chapter 4 in our physics textbook. We have been looking at force causing acceleration and leading up to Newton's second law of motion. Don't forget to keep looking at your vocabulary words. This video is going to look specifically at free fall, and it is a review with a little bit of new added, but you worked hard on the last chapter on free fall, and it makes sense to you. So we're not introducing anything different with free fall. We might look at it a couple different ways, but you already understand free fall, and that is when the only force acting on a moving object is gravity, acceleration due to gravity. Now we already know this, that when we've got two objects free falling, that their acceleration is going to be the same, and that is conveniently 10 meters per second squared. Okay, more precisely 9.8 meters per second squared. But we know that this happens irregardless of the mass, the size of the object. Let's look at it relative to Newton's second law, because we know that when we drop things off the top of the roof, we will have more massive objects than other objects. And fundamentally, we know that they land at the same time, but what's going on with the fact that one is more massive than the other? Well, what's going on here is that an object with greater mass has a greater force of attraction relative to the Earth. Gravity is pulling it. There is more mass that gravity can use to pull. But counteract that with the fact that the more massive the object, the more resistant it is going to be to that movement. The more massive object is more sluggish. It takes a greater force to push it, and those balance exactly. So the acceleration is the same regardless of the mass. All right? Think about this for a minute. We already know that accelerations are the same, and it's constant due to gravity. But another way to look at the same thing is the relationship between the force and the mass gives us the same acceleration of gravity g. Two different ways to look at the same thing. Let's practice this one. We have an object in free fall at 40 meters per second at its instantaneous velocity, or its speed 1 second later. So the only force acting on it when it's free fall, the only force acting on it is gravity. So if it's at 40 meters per second, a second later, its speed is going to be the same, unchanged, increased by 5 meters per second, increased by 10 meters per second, or none of the above. This is the exact same problem that you worked in chapter 3. 10 seconds later, this speed is 10 meters per second faster because we are accelerating at a rate of 10 meters per second squared. Same problem we worked. Go look back at some chapter 3 videos if you don't remember how to solve that problem. Okay. There's one thing though that we didn't do in solving this, is that we did not draw our free body diagram, and we did not look carefully at the wording. So you may have we just kind of assumed that our free fall situation was somebody dropping something for example, from a roof. Okay? It doesn't say that because it is talking about speed. And remember, speed does not give us a direction. So there's another answer to this problem if all that we know is what has been stated. An object in free fall has a speed of 40 meters per second. There's no direction given. So maybe our assumption that we are dropping this off the roof is wrong. We could have thrown it up in the air, at which case it's the force of gravity would be opposite of the direction, so our speed would decrease, not increase. So what's the other answer to this problem? Now that I've clued you in, if you read it again and say, at one instant we have a speed of 40 meters per second, what is the speed a second later? Well, if its direction of motion is upward and gravity is pulling it opposite of that, then we would be 30 meters per second. All right. A little example about why vectors and drawing diagrams and knowing directions of your forces makes a difference for you. Let's look at another one. We have, let's go back up on our roof, or maybe we're standing on a table, and we're going to drop 2 iron balls. One of them is more massive than the other. And we'll assume negligible air resistance. What's the acceleration of the heavier ball? Is it less? Is it the same? Is it more? Or do we not know enough to answer this question? So we're dropping 2 objects of different sizes, of different massiveness off the roof. What is their acceleration relative to each other? Acceleration is the same. Acceleration is the same. Okay, we're dropping the same 2 balls, and the speed of the smaller ball is at 10 meters per second. What's the speed of the ball falling with it? When one ball reaches 10 meters per second, what is the other ball doing? The other ball is at 10 meters per second. We are in free fall. The speeds will be the same. Again, this is a review of what we've done in Chapter 3. Our next video will look at the situation of non-free fall. So in the situation where there are forces in addition to or other than strictly gravity.